questions?
Maybe one.
Mm-hmm.
I don't know if it's connected to the current topic, but do you know any methods to like stabilize problems when we've got no boundary condition for the velocity, but two boundary condition for pressure? So let's say we want to say that at the inflow we've got pressure that is bigger than on the outflow, and we have to solve that. And I think one solution that I've read some time ago at the CFD online was like just start with small difference and then increment the difference between inflow and outflow. But I was wondering if
I'm afraid it won't help much.
Okay.
Like you can use this boundary condition not only as outflow, you can use it as inflow. It will work, but like this stability is limited by, so to say, velocity and viscosity. So if you go with a bit higher Rayleigh number, this will probably diverge. There are ways to stabilize that. To be honest, I don't know them. I think maybe even Adam knows some of them. I think Kuba was experimenting with.
Kuba was doing something with porous media.
Yeah, so there exist. I haven't been playing with them around, so not from my head. Okay. The last thing that I want to mention is this mess with the vector notation. And let's start with I want to make it quite evident for you how you implement the problem. Let's first imagine the vector of unknowns. We want to have ux, uy, and pressures P. And on purpose, I show that ux and uy is longer and P is a shorter vector because you've got like second order, you've got many more nodes for the velocity representation and less nodes for pressure representation. But then the matrix structure that will come from that is, what do you have here? Again, we've got the mass matrix plus diffusion matrix plus convection matrix, mass, diffusion, convection. Here we've got something that implements the gradient with respect to the this one needs to, the whole block needs to implement the gradient operator applied to the pressure. So there is like the x component of the gradient operator and y component of the gradient operator. How do you test the vector problems in finite elements? Like once we had the scalar problem, for example, 0, or something like that. Like we had no problem. We said, okay, let's use this test function which v will be equal to some phi, and that's already, and we can quickly move to the discretization, and it will be our test function. Now, how do we generate the discretized version for vector problems in finite elements? Well, this one is correct because you really are using vector test functions. But what are you interested in? You're actually interested in generating a scalar equation for the first component and a scalar equation for the second component. So, well, you could have probably multiple choices how to discretize that. But what is always done is if you've got a vector problem, you replace this V by a vector test function such that it's phi 0, because what it does, then see, well, phi is as usual our test function, scalar test function. What it does, just see, if you've got ux, uy times a vector test function, and you've, well, accidentally chosen the test function to be like that, then something like that, like selects in such a way that such a test function will generate the scalar equation for the first component of your unknown field. Okay? So you use such test functions to generate all the rows and equations here for the first component. Then you say, okay, for the y velocity component, we are testing the field with different test functions. What kind of test functions? 0, phi. Then obviously, such a test function will select everything that is associated with the second component. Well, and then we loop over the rows and generate the next equations. And that's how you quit discretizing the velocity equation. Okay, so it's very important that you remember this concept that if you deal in finite elements with the vector problems, you've got the strong formulation in the vector form using the dot products, but you simply, during the discretization, you replace the test functions by actually scalar functions for one component or the other component. They generate scalar discretized equations for the first component and for the second component. Like we could spend a couple of minutes to really think about that, where you need to put the arrow and where not to have it mathematically in place. I don't want to spend this time. I much more want that you understand how to do it.